MS Ramaya University of Applied Sciences.
Hi students, let us discuss pulse code modulation and demodulation. The aim of the experiment is study of pulse code modulation and demodulation. In a brief sentence, pulse code modulation is a method used to convert an analog signal into a digital signal so that it can be transmitted through a digital communication network and then converted back into the original analog signal. The PCM process includes 3 steps: sampling, quantization, and coding. Pulse code modulation is having sampling, quantizing, encoding as steps. The apparatus required are Syntec 2153 and 2154 kit with power cords, digital oscilloscope, probes, and connecting cords. The procedure is: ensure the following initial conditions on the Syntec 2153. Mode switch in 320 kHz position or fast mode. DC signal 1 and DC signal 2 controls in function generator block fully clockwise. 2 kHz and 4 kHz signal controls set to 10 volt peak to peak. Pseudo random sync code generator switched off. Error check code selector switches A and B in A is equal to 0 and B is equal to 0 position or off mode. All switched faults off. Connect on Syntec 2153. DC signal 1 output to channel 1 input, DC signal 2 output to channel 2 input. Turn on the power. With the help of digital voltmeter or oscilloscope, adjust the DC signal 1 amplitude control until the DC signal 1 output measures 0 volt. The accuracy should be within plus or minus 20 millivolt. Turn the DC signal 2 amplitude control fully counterclockwise. Observe the output on the analog to digital converter block LEDs D1 to D7. The LEDs represent the state of the binary PCM word allocated to the PAM sample being processed. An illuminated LED represents a 1 state, while non-illuminated LED indicates a 0 state. D7 is the MSB and D1 is the LSB. The LED output looks as D7 1, D6 is 0, D5 is 0, D4 is 0, D3 is 0, D2 is 0, D1 is 0. This output is the digital representation of 0 volt input to channel 1. Adjust the DC signal 1 amplitude control clockwise to increase the amplitude and anti-clockwise to decrease it. Try varying the DC input from plus 5 volt to minus 5 volt in steps of 1 volt. Take care that the input value is within the specified range of plus or minus 20 millivolt. Observe that the output for plus 5 volt is as follows. D7 is 1, D6 is 1, D5 is 1, D4 is 1, D3 is 1, D2 is 1 and D1 is 1. Where for the negative values it is less than 1, 0, 0, 0, 0, 0, 0. For minus 5 volt the output is as follows. D7 is 0, D6 is 0, D5 is 0, D4 is 0, D3 is 0, D2 is 0, D1 is 0. This is obtained at the approximately full anti-clockwise position of the DC control. Turn the DC signal 1 control fully anti-clockwise and repeat the above procedure by varying DC signal 2 control. Check that the digital code for the set voltage value is identical to that of the DC signal 1 setting. Once again, take a precaution of maintaining the set input within plus or minus 20 millivolt range of the specified voltage. Switch off the tech book, disconnect the DC signal 1 and DC signal 2 supply from channel 1 and channel 2, connect 2 kHz signal to channel 1 and 4 kHz signal to channel 2 input. Figure 6.1 shows 2 kHz and 4 kHz sine wave output in dual mode. Trigger the dual trace oscilloscope externally by channel 2 signal available at 4 kHz sine wave at function generator block on Syntec 2153. Observe the signal at channel 1 unity gain buffer amplifier's output with reference to the SC signal output of PCM timing logic block on the second trace. Give special attention to the phase relation between the two signals. Now connect the oscilloscope channel 1 Y to channel 2 unity gain buffer amplifier's output and sketch the three waveforms with utmost importance to the relationship between the three waveforms. Connect oscilloscope channel 1 Y input to SC signal output and oscilloscope channel 2 X input to EC signal output of PCM timing logic block of Syntec 2153. Observe the phase relation between the two SC and EC pulses. Now notice that EC goes high at the end of the conversion and remains latched until next SC pulse.
Hi students, current experiment is pulse code modulation and demodulation. For this experiment we are using the Syntec 2153 and 2154 board. This is Syntec 2153 board. Here we are having the pulse code modulation scheme. First, the sample and hold output of the circuit is converted into digital bits, zeros and ones, using the analog digital converter, and once the analog digital conversion is done, we are using the parallel to serial conversion such that we can transmit bits serially over the channel. The output of this PCM modulation is this point, TDM PCM output. Then in Syntec 2154 we have the PCM demodulation block. Here we are connecting the TDM PCM output to the TDM PCM input of Syntec 2154 board. Here we are having serial to parallel converter using the shift register, and then it will be converted to the digital to analog conversion, and it would be channel 1 and channel 2 slots will be demultiplexed and processed, and finally it would be low pass filtered, and then we are going to get the channel 1 signal as well as the channel 2 signal in separate. And digital oscilloscope, this is digital oscilloscope. Main power switch of this digital oscilloscope is this one, and we have this is a two channel oscilloscope, channel 1 and the channel 2. These are the magnitude adjusting knobs, and these are the horizontal position adjusting knobs, and this is the time scale adjusting knob. These are the connecting probes for digital oscilloscope, and these are the connecting wires for the Syntec 2151 board. Now let us start the connection for the experiment pulse code modulation and demodulation. Take the connecting wire and connect the DC signal to the channel 1 input, and connect the 2 kHz sine wave to the channel input 2. Then connect the TDM PCM output to the TDM PCM input of the adjacent board. I am creating a common ground for both Syntec 2153 and Syntec 2154 board. I am connecting the ground of 2153 and the Syntec 2154 ground. I need to have the common synchronous clock between the two boards such that I am connecting transmission clock of the board 1 to the transmission clock of the board 2. Take the connecting probes for the channel 1 and channel 2 of the oscilloscope. Connect the channel 1 probe to the output of channel 1 and the ground, and the channel 2 to the output of the channel 2 and the ground. This completes the connection. Let us switch on the power supplies of the board as well as the digital oscilloscope. Now we could able to see the transmitted waveform, sine waveform, and as well as the DC signal. Here if I vary the magnitude of the sine wave in this board by varying this knob, varying the 2 kilohertz signal generation magnitude knob, so we can see the variation in the magnitude of demodulated output. So this shows that modulation as well as the demodulation is perfect, and we are seeing the same sine wave which is transmitted as well as received. When it comes to the DC, observing the DC signal in the channel 1, I need to vary the DC magnitude. By this varying this knob, I could able to see the variation in the demodulated signals. This is channel 1 signal magnitude, that is blue line, blue signal. Since our eye resolution is, if a bulb switches on and off more than 16 times a second, our eyes, human eyes fail to recognize the on and off of the bulb. So these small LEDs appears to be glowing all the time. But in reality, if I reduce the sampling frequency of the pulses from 320 kilohertz to the 1.9 hertz, so I could able to see the on and off states of the LED such that its operation can be observed, like analog to digital conversion operation as well the serial to parallel conversion operation. When it comes to this board, it is back to the serial to parallel conversion as well as the analog to digital to analog conversion. This completes the experiment.
At MSR, you mark your imagination.